next Monday, we are going to hold a very, very easy and, a almost nothing kind of a quiz. So I can again see Anjana and then Arpan. So next Monday, there will be a quiz, 15 questions, MCQ type. So you just tick one answer, right answer. And then 5 questions, which will be either a one-word answer or a one line at the max is the answer. And so 20, and we'll give you an hour. So we start at 4:30 and you finish it by 5:30. I mean, you will not need more than probably 15-20 minutes. But anyway, we'll give you that. And it will be taken on a Google form. So basically, you will be sent a link in the email ID, email address that we have. And the fact that we have the right address, just for that, a test mail will go in a day or two. So I would request you to simply send by reply mode an answer to it, just saying okay or anything, that you have received it, because that's the mail ID where we would send the link for the exam on next Monday, 25th, starting at 4:30. So we will be obviously taking, we'll be counting 4:30 as the beginning of the exam. And after 5:30, we will not entertain any answer. And you will go through the questions and the total exercise. You will see it should not take more than 20 minutes, half an hour for all of you. So with that, I will just introduce today's speaker, who is Professor Mrinmay Mukhopadhyay. Mrinmay is a very important component of these kind of exercises where we are talking about emerging trends in biophysics. Mrinmay is an out-and-out physicist, a condensed matter physicist, and or these days probably they use a word called soft. So he is a soft matter scientist. Probably that would satisfy him. It's not that he doesn't do hard matter. He also does a real, I know him very well. So he is a person who is our, X-ray and neutron scattering person. And he has worked, he has experimented in name any of the world-class synchrotron facilities that exists in this globe. He has gone there and done an experiment. Second thing is he was doing his postdoc in Northwestern University once, and then he had a stint in the photon factory at KEK. And I must mention that actually there is an Indian beamline, and Mrinmay is the person who has actually, did everything, that, starting from designing to fabrication and everything, which is still working. And Mrinmay is also very closely involved with that beamline at the Indian beamline at the Photon Factory, Japan. So with this, Mrinmay, you can start your class, 2 classes, and I leave. All the
Okay.
best.
Okay. Thank you, Abhijit. Thank you for nice introduction. I don't know. Okay. So let's start this thing with the sharing of my slides, because it is not a chalk and board kind of class today, but let me try if I can convince you that X-ray and neutron scattering techniques are one of the fundamental and one of the useful technique for your biophysics research, as well as compared to, I will say, in condensed matter or any other things. So what I will be talking about is X-ray and neutron scattering applications to study biomaterials. So my name is Mrinmay Mukhopadhyay, and I am from Surface Physics and Material Science Division in Science to Nuclear Physics. As you can see, this it doesn't say any bio, but it's basically, as Professor Chakraborty said, we work in biomaterials, and what that biomaterials using the techniques in condensed matter that we used in condensed matter over the years. But now X-ray and neutron scattering, you cannot say that this is a pure condensed matter techniques, because it's a, you can, if you can go through the Nobel Prize list, then probably you can see that at least 2 Nobel Prize gone through bio stream, where X-ray and neutron scattering are the prime source of technique that was used. So I will be talking about, let me frame my lecture first. Why it is not moving? Yeah. Okay, so there will be 2 lectures. One is first part. So I said first part and second part. So first part, I'll talk about basic understanding of X-ray and neutron scattering. Then in X-ray and neutron scattering, one of the most important thing is the scattering geometry. So because I'll explain these things in more details, but I'm just giving you a glimpse of what I am going to say. So scattering geometry, it's not like microscopy where you can see the real images of your sample, and then you can judge your sample, what you want to do and what you want to see. But in scattering, we get the information in reciprocal space. And what is reciprocal space? That probably you all know, and I will explain it in my talk in detail. And then I will talk about that, and in that scattering geometry in reciprocal space, basically what you want to study is very important to go where you want to be in the scattering geometry. So basically, it's a reciprocal, and it's a toggle between reciprocal and real space. So if you want to see something in some length scale and some information in some surface or interior, you have to go in some other geometry where you can get this information. So it looks like it's a puzzle, but it's not. I'll explain those things. And then advantages and limitations of these techniques. Every technique has some limitation, and X-ray and neutrons are basically also will have some limitation. And one of the main limitation is for X-ray is the damage. So it damages the sample, and because of high intense X-ray photons. So if you go for low intense X-ray photon source, then you will not have enough scattering data so that you can basically get back your information. But if you go in high brilliance source where you have a lot of photons, means I am talking about 10 to the power 14, 15, 18 photons per second within some area per unit area or this kind of thing. So, and then I'll talk about the X-ray and neutron reflectivity technique, which will be used for understanding the biomaterials. And the second part is my X-ray and neutron are important for biological samples. So why it is important, and what is the complementary role of X-ray and neutron reflectivity, and few applications. So basically, second part will be more on kind of application to the biosystems, and the first part will be more on what is X-ray and neutron scattering. So these are the combinations. And so I hope you will enjoy this and then you can have some better understanding, and then you can, in future, you can explore more to do this kind of research. Okay, so first, as a basically, what we like to do, we get a sample. Suppose we prepare a sample and we want to know about the sample so that we can predict the physical phenomena. And physical phenomena means, suppose I am studying some polymers, then I want to know what is the rheological property, what is the stickiness, what is basically the suppose a lot of things are prepared and now are polymers, and then in some cases hardness is important, and in other cases hardness is basically softness is important. So those are the important things, and how you can predict that the sample you are preparing can actually show this kind of physical phenomenon. And so for a characterization of sample, we need some like elemental composition, and we need to know the structural composition, or we need to investigate the structure. And then the dynamical behavior. Dynamical behavior, it means I am talking about, suppose you have a dynamic process in your membrane or in your biosystem. So, and you want to investigate the change in the parameters as a function of time, and that's we call dynamical behavior. And there are many more like this. So we need to predict about our sample to explain the physical phenomena, and that's why we say we need to characterize. And moreover, if you have a surface dominated systems like nanomaterials, and nowadays it's a nanobio is a famous word, and so these kind of systems, then we need to know we need to know about the surface activity or surface of the material, so that we can, because if you see that catalytic property is mainly dominated by the surface activities, and the surface activities you can actually determine or characterize using your characterization technique methods, different methods. So what are the major categories of these characterization techniques? So there are, you can actually touch. So that's basically contact method versus non-contact method. So you don't want to touch your sample. And for biosamples, this is the case. You don't like to touch your sample, because if you touch, then you might damage the structure, or you might change the environment or something. So there is always a competition between contact mode and non-contact mode of characterization techniques. And there is also another mode that is called destructive method of characterization and non-destructive method of characterization. And X-ray has a role in both the cases, because X-ray photons, X-ray or neutrons, I will say X-ray and neutrons both. So that is a non-contact mode of method, because it is a tiny part, neutrons are tiny particle, elementary particles, and then X-ray is a photon. So basically they don't touch the sample really, where you can change your sample environment, or you can destroy your sample. But it is a non-destructive method. So as I said before, that it damages samples. It damages sample, but there are several ways we can reduce the damage. So, and simply destructive method, we means that by the end of the day, end of the measurement, we destroyed the sample. That is, we call destructive sample. But if we follow certain protocol, if you follow certain process, then we can actually, X-ray and neutrons are non-destructive. And neutrons are very, very helpful. Neutrons are mostly non-destructive method. So X-ray and neutrons are in the category of non-destructive method and non-contact method of characterization technique. And then there are examples of other non-contact characterization techniques like X-ray and neutron reflectivity, X-ray photoelectron spectroscopy, So basically, you can say that electron spectroscopy or SCA or XPS. So these are different characterization techniques. You don't need to remember all these names. Wherever you want to know about the specialized techniques, then you can go. And each technique probes a certain part of your sample, certain characteristics of your sample. Because if you want to see the X-ray photoelectron spectroscopy, then you are probing the local electronic environment of your sample. Whereas if you are probing X-ray neutron reflectivity, you are probing the average information of your sample along the perpendicular growth directions. So these are different. That's why I said that you have to choose what you want to do, and then accordingly you can choose your characterization techniques. And so X-ray, it is all X-ray. I am talking about X-ray and neutron, but still, if you are probing some local environment or global environment or some electronic properties or some other information, structural information, then you have to go in that mode of operation, and then only you can get the information. So basically, our first job is to that where you want to get the what you want to get the information from your sample. And then if you identify that, okay, I like to know the size of the nanoparticle, then I have to go in certain geometry and do the measurement. If I want to know, okay, I want to know the thickness of my film or the thickness of my vesicle, then I have to go in certain geometry to do that measurement. So that's why I am telling that each geometry is important, understanding of geometry is important, and then only you can go in particular technique to do the X-ray, use X-ray and neutron characterization for your system. So there are other characterization techniques like electron diffraction, and this is very well known for the who work with scanning electron microscopy or transmission electron microscopy. So these are basically microscopy based techniques, so you can actually see the sample surface and or topology or the a little bit of inner elemental information. So these are microscopy, so you can see the real image and then you can talk about your sample. But in diffraction or these XPS or XR or neutron reflection, so these are, or electron spectroscopy, these are information in different domains. So you have to basically model your system and then only you can talk about your sample. But the richness of your data is actually dominates so much that these are so much popular today to explain your or to characterize yourself. So these are the basically different characterization, non-contact mode characterization techniques. And out of that, I have marked two points, that one is SIMS, another is cross-sectional TM. So these are called destructive methods. So out of other things, those are basically non-contact mode, but and as well as non-destructive. But these SIMS and TAME, cross-sectional TAME, these are destructive because you are actually cutting your sample or you are actually eroding your samples with the measurement. So that's why these are marked as a destructive method of characterization. And then there are contact mode of surface characterization is the atomic force microscopy. This is well-known technique, and probably most of the scientific institutes or universities, everybody has this kind of atomic force spectroscopy or active instrument. And scanning electrons, scanning tunneling microscopy is also another mode of surface characterization or sample characterization method. So sometimes, okay. So microscopy. So this is well known that what is the structure of the sample surface and lateral. I have some, because a lot of people and you people also use this confocal microscopy or visible microscopy, and you have a lateral resolution, you have a vertical resolution. contrast mechanism. You always play with those things and try to minimize your effort to maximize the information you can get from the sample. And then it has a dynamic range and all the XA2, in situ, all these kind of technique, all these kind of measurements you can do. So here is a length scale, basically 1 angstrom to 1 centimeter I have marked. And then we have several things like here, which is 0.1 micromillimeter. And then you have red blood cell, virus, computer circuit, molecules, atoms, all these things. These are well known. And then you know these are, and what we want to know now. Now, let us put some questions. What do we need the X-ray and neutron as a probe for scattering techniques? Because first thing is, why X-ray? Why neutron? Because there are several other probes. And what are the other probes? And how does it stand with respect to the other probes? So basically, you have to first convince yourself that, okay, I need X-ray and neutron as a probe for measurement, characterization measurements. And then you need that what else you can use and how it is different, or what respect you can use this as a probe instead of some other probes. So these are the three basic questions that you should ask when you are characterizing with your X-ray or neutron as for your system. So what are the probes? So elementary particles are good probes. So that we know. So elementary particles means basically neutrons. So why I have used this 4 instead of, I will not go for with a iron 56 with a as a probe for my instrument, for my sample, because then that instead energizing that iron itself is a big job, and then it will be basically interacting with my sample. So there are a lot of problems. So instead of doing all these, I will go smaller particles, and smaller particles means I have neutrons, X-ray, electrons, and ions. Ions of few materials, so like argon, like helium. So these kind of small charge ions I have. So we know neutrons as an uncharged elementary particle, but it has a mass. Neutrons has a mass, but X-ray is also a uncharged part. You don't need to say it's a particle, but it's a radiation. And the advantage of it doesn't have a charge. So we have a charged particle, we have an uncharged particle with mass. We have a uncharged and no mass particle like X-ray. We have a charged particle like our electrons, and also that has a mass, very less amount of mass. And then we have a charged particle with mass and as a big mass. So basically all these, you can cover all this with these kind of these 4 particles, 4 probes, basically neutrons, X-ray, electrons, and ions. And all of them can be used to characterization depending on what you want to measure. So this is the important thing that I want to say, that these are all important probes and each one has advantage and disadvantages with respect to what you want to measure. Suppose, for example, X-ray doesn't have a charge and doesn't possess any mass. So that means if I go back to my school days, quantum mechanics or classical electrodynamics or this thing, then I can work with Maxwell's equation for X-rays. Whereas for neutrons, I have a mass, and electrons, I have mass. So I can work with Schrodinger equation for the neutrons, and then, or Helmholtz equation for the neutrons. And then I have a charged particle here. So the problem with that the charged particle interacts with the charge of the system. So basically now you have to include Coulomb interaction. And then you have ions where you have to include Coulomb interaction as well as you have a definite mass. So you have to use Helmholtz equation or Schrödinger equations to solve your boundary condition or your wave equations, which I will be coming in a few minutes. So basically, these are the 4 probes. And then I have my particle wave duality. Sorry. So you can see that energy is hc by lambda. So h is a Planck's constant, c is basically velocity of light, and then lambda. So energy. So if you increase your energy, your lambda will decrease. So basically, X-ray photons. If you increase your energy, your lambda will decrease, and this will go down simple by this way. And then you have a neutron, so you can do that the same thing same way, and electrons also can be done the same way. But now you have a mass here, so for electrons and neutrons you have to use this formula. So for photons you can use this formula because it doesn't have mass, and for electrons and neutrons you have to use this formula to calculate your energy, and that can be done easily. Okay, now what is the range of X-ray? Because I will be talking about that range of X-ray is something like 1.1 angstrom. You can go very hard X-ray to a soft X-ray, which is about 100 angstrom or something like that. So basically, you can tune your X-ray energy depending on what you want to measure. And similarly, you can tune your neutron and electron. So you can say, well, we can use electron, we can use neutron, we can use X-ray. So why we need 3? Because all has some advantage. Electrons, we can actually produce a lot of electrons from a source. We have very good source of electrons, and then we can have a lot of intensity of electrons compared to number of neutrons or number of X-ray photons we can produce. But electrons has the problem of charge. So if you are using a non-conducting sample, then basically that electron beams will charge the sample and then it can change the whole environment of your sample. So you don't like to do that. For non-conducting sample, you don't like to probe it with the electron. But if you have a conducting sample, then you can actually use electrons. And then you have a neutron and X-ray photons. Then I'll show where it is the advantage of X-ray and where is the advantage of neutron. That I'll come to your in a few minutes. So differences while probing the surface. So you can particle mass wise, these are basically the thing. And the rule is that rule of thumb that we use, heavier elementary particles scatter from lighter. So that's why if you want to use the your sample mostly made of hydrogen and carbon, lot of time we use ions because ions scattering cross sections are much higher, whereas for photons scattering cross sections are much less for those kind of things. And obviously electrons and neutrons are in between. So basically this is one kind of selection that what probe you are to use is, if you like to use a specific role of some elements, you can see whether it's a lighter element or it's a heavier element, and depending on, you can choose your probing material basically. Okay, now how we do these experiments. So it doesn't depend on what kind of probe is. It is we have a electron neutron incident particle, electron neutron photons and ions. It's coming to the sample and we have to detect. So we can detect the sample as a whole. Basically, if we say we can say we give 10 photons on a sample and how much it is coming, this is one way. How many of photons are coming out? We can say that what is the phase difference between the photons which is coming out, what is, then we can talk about the dynamics of the sample. Then also we can say that how many are absorbed in the material, and then what is the excitation energy. So all these things, but ultimately you have a probe and you want to see the outgoing particles response. So this is the common method of any scattering measurements. So you will come up with a source of your probing particle, and then you have a sample, and then you have a detection unit where you can detect the probing particles, the outgoing probing particles. So a scattering, any scattering experiment will involve these three: a source, a sample, and a detector. So, and then you can arrange whatever way you can do the measurements. So, that is what I was telling, that it started with X-ray. So, X-ray techniques probably the grabbed maximum number of Nobel Prize that is so far. So you can see that Röntgen discovered this X-rays in 1895, not in 1895, it's 1864, and then it got Nobel Prize in 1895. Then you have a first diffraction, so basically first X-ray image of your of a real hand, and then you can actually brag got this crystal structure. So how you can extract the crystal structure. Then it took over by biologists. Then you basically solved the DNA structure using X-ray, and recently solving the ribosome structure by Ramakrishnan, Ada Yonath and all in 2009. So basically it started a long back, and it is a very useful technique to understand the structure of your material. So that's what basically the important part of this slides. How we do? We have a X-ray unit source. So basically we have a source. It can be X-ray, it can be neutron, it can be electron, what doesn't matter. You have a sample, and then you have a image photographic plate where you can see the spots, and depending on, and from that spots you have to back calculate to get the information. So the theory of all the development or all the analysis part is basically to get back the information of your sample from this image or from this scattering profiles. So as I said, that it is not a real space image of your sample. So whatever your sample is, you don't see this is coming here. So your sample may have some different crystal orientation, but it will show some other orientation, other diffraction images. And then you have to have some methods to go back so that you can predict your sample information. And that's why you need to learn how to get back that information. Otherwise, X-ray experiments are not so difficult. X-ray experiments are basically, you can see that you have a source or X-ray or neutron. You have a source and then you have a sample and then you get with the image. So that experiment-wise, it's not that difficult. It's a very simple. In microscopy, you have to adjust a lot of things and then you can get the best image you want. But in X-ray, you just put your sample and then you can get the image, or you can get the image of a scattering image of your sample. But what is exactly, it will look like this, and or it will be some profiles, and then you have to have some mechanism to get back the information of your sample depending on your this image or profiles. So that part is tricky, and I am going to talk about that. What are the information you can get from this? And in terms of resolution, X-ray is pretty good that you can go like 0.1 angstrom change to some micron. So basically, it's a huge resolution, lateral resolution or vertical resolution, whatever you say. It covers very wide range of your sample, and this is the beauty. So in ACM, if you start, you just be around this one, whereas if you are in a lateral resolution, you are something around nanometer range, but in vertical resolution, it's very poor. But in X-ray, you can have a lateral resolution and vertical resolution, both in a very modest area where your sample basically virus, bacteria, and all are the condensed matter, subcondensed matter, biological samples, lipid, proteins, all lie in between. So basically, X-ray and neutrons are in that way very good technique to probe this kind of, to resolve those kind of structures. Okay, so here I am going to talk about some mathematics. You don't need to go through the mathematics in detail, because these are a kind of a little bit of calculation where a simple presentation will not work. You have to do it by hand over a chalkboard and other things. So, but here, if you understand the physics, and that should be good enough for at this moment. So what I am trying to say here, that you have a plane wave. You know this plane wave. Plane wave, we basically in physics, because you all had physics in element plus 12 and BSc or in graduation. So you know plane wave, we write e to the power I k dot r. So this is a simply e to the power I k dot r, or you can write I k dot r minus omega t. So this kind of expression we have used. And now we basically it's a plane wave. So this is the kind of plane wave front. I can say that a plane wave is coming. Then what will happen if we have an electron? You have an electron here, then basically it will interact and it basically starts to oscillate. And then an oscillations will give radiation. So that radiation we are actually looking at. So how X-ray interacts with the material? So we have a wave of X-rays, and then that wave is hitting an electron, and that electron starts to oscillate. And then because it got the energy, and that energy it will starts to oscillate, and that energy, because of that oscillation, it will radiate energy. And by this process, it will lose the basically incident energy that it got. So if you see that you can calculate this radiation energy by simply by doing this, basically here it's a cos psi. So this direction it will see, or you can go along this direction. So you can go along the beam direction. So this is the beam direction. I can go to a pointer, laser pointer. So you can, this is my beam direction, and this is my electrons. And then you can actually go along this direction or in this plane. So what is important now? I am going towards the geometry of the measurement, because here your plane of your measurement is basically consisting of this incident wave, the oscillation of the electron, and the scattered wave. So basically this is my incident wave and this is my scattered wave. So all these are in the plane of your measurement. And in this case, it is the opposite. It is the incident wave is coming and the scattered wave is at the vertical. So we call it in plane, and this is we call in vertical. So instead of, so one case we are measuring in the in plane direction, In another case, it is going upwards or it is in the out of plane direction. It can be not only in this direction, it can be along this direction in an inclined way. That in that case, you have an in-plane component and the vertical component. So that's we call the geometry. So where you want to put your detector? You like to put the detector here, which is just in this vertical plane, in the same line as in the incident wave, or you can put your detector in the in-plane direction, in this in the same plane, or you can put in arbitrary area where basically you can have in-plane and out-of-plane components. And then you can actually solve these equations, but important point is this here is the R0. R0 is equal to Thomson. We called it classical electron radius. Here you can see that instead of so your incident wave was basically I was telling into e to the power ik dot r. So that is my incident wave. So I am not doing calculation. I am just explaining you what the physics. The physics is your incident wave is e to the power ik dot r. Now, at a certain distance, it will be e to the power k dot r by r because it is propagating in all directions. So basically, it will go over 1 by r. So e to the power ik dot r by r. So this is my in a certain direction, in any direction, you just go and you will have the component of e to the power ik dot r by r. And then you have a factor which actually is a angle of your movement of the detector. So where you are measuring. So you have an angle which is cos psi. It can go to 0 to 1. So basically it's what angle you are measuring. We call it polarization. I will come to that point. But important point, if you just for the time, if you just forget this cos psi at this moment, so your irradiation, a radiation wave is basically another plane wave which is multiplied by a factor. So this factor we call it R0 and that is called it, and throughout my lecture I will be using this term R0. And that is basically, we call it classical electron radius. So we have a incident wave e to the power ik dot r at some point r. Basically, this point you can say it will be e to the power ik dot r divided by r times R0. So you can forget all the other calculation. Then you can say my radiated wave will be R0 times the incident wave. So that's the physics I want to say, because I am not going through the calculation. So you can only remember that part, that irradiated wave will be R0 times the incident wave divided by the distance where you are talking about. So this way you can actually calculate the scattering cross section. And then you can see all these calculations you can go through, but I am not going through this one. I am just telling that you basically say it's R0 square times P is a polarization factor, which is basically cos psi dependent, and that we will be talking about later. Polarization you people have used, must have used in a lot of polarization in optical instruments like your confocal microscopy or imaging microscopy. In any, you can use polarized light. So similar to that, your X-ray is also a light, right? So X-ray also has a polarization factor, and that also has significance in the scattering. So you don't need to think about much about at this moment. But important thing is that R0. R0 basically you have the incident wave, and the outgoing wave will be R0 times the incident wave. So that's the calculation you can think of. And then you can carry on this thing, because your system doesn't have one electron, but your system has consists of multiple electrons. And then you have a, so I will go one by one. So like instead of electrons, and now I have taken atom. And then you can think of a structure, atomic form factor. So basically F0Q, which is a electron cloud of the whole atom. So this F0Q, you can see that, you can think of that this is an electron cloud of the of your system, and then you are basically just electron cloud is, you can think of atomic form factor, and then you multiply it with R0, that is your term. So R0 times F0Q is your, so is your total scattering term. So there are other things. I am not, because I don't want to go into the details of those these items. Otherwise, because in X-ray there is another thing is that if it matches with one of the energy cells of the core electrons, then you have basically you are knocking out electrons from the core cells, and then you have another radiation coming out, which is called characteristics lines and all these things. So X-ray can actually knock out electrons from the core levels, and that will give you this kind of energy dependent terms in your scattering. So at this moment, I can forget these terms, and I can simply consider F0Q as my scattering atomic form factor. And then you, instead of electrons, now I have a, just think that one plane wave was coming e to the power ik dot r. The scattered wave, I said R0 times e to the power ik dot r by r. So that is done. Then I have a, instead of electron, I have now an atom. Then instead of one plane wave, I have multiplied R0 times atomic form factor. So that atomic form factor actually can tell you the information about your atoms. So this way we can carry on, and we can say that, we can say atomic form factor, then molecular form factor, and then structure factor, lattice sum, all these things we can slowly one by one we can calculate. And then we can end up having a crystal where you have a unit cell structure factor, then lattice sum of all these things. And so these are simply the crystal structure, and you can actually dig out the information of your sample. And then simply 2D sine, this is the famous law, 2D sine theta is equal to n lambda. Because if you think about your protein crystal diffraction, then basically this is the formula used, 2D sine theta is equal to n lambda, and you can call this thing as a, you can extract. So and the D, and then you can talk about your sample crystal orientations, crystal configuration, on all these molecular orientation, everything. So basically these are the basics of X-ray scattering. And now what I am going to talk about the scattering geometry. So this is the information, very important information for your sample, for your measurement. Because initially I started with the point that what I like to investigate is very important to identify where I will go for these measurements. Okay, so now if you say, if you, this is your higher secondary, in Specular book, you have vector analysis. You must, everybody we have read this book, vector analysis by Specular. And so there we have a simple calculation. So calculation is that one is components of a vector. So components of vector means one, if one vector is coming like this, so which is basically now my incident wave, then we can actually, because if it is a three-dimensional geometry XYZ, then we can have a QX component, QY component, and QZ component. So what is Q? Q is a wave vector transfer. So Q is basically a characteristics of my e to the power I k dot r. I said initially, right? So that k, Q and k is basically ki minus kf. So ki minus kf is my Q. So basically incident wave and exit wave, the difference between wave vector is wave vector transfer is Q, and that Q can be this vector can be divided in three components: Qx, Qy, and Qz. And this is a simple calculation you all can do in your home, that Qz is equal to 2 pi by lambda sine theta I plus sine theta f. So whereas theta f is this. Qx also you can do, and similarly Qy you can also calculate. But I have plotted a basically diagram where this vertical axis is my Qz, and the horizontal axis is my Q parallel. Q parallel is basically Q root over Qx square plus Qy square. So I will say why it is I said parallel. Parallel is my in plane. To designate it as a in plane. So basically, if you remember my original slide, that I said that one wave is coming and then one wave is going out. So whether you are measuring that the wave is going out in all directions. Now, your detector is in the plane of your measurement of your sample or in the vertical plane. So this is important. So in the plane, so if you now divide Qx is along this direction, Qy. So Qx and Qy both are in the plane of the sample. So that's why we call it Q parallel. So Qx and Qy both are in the plane of your sample, and Qz is along the vertical line of your sample. So that's why we can say Q parallel, which is basically Q root over Qx square plus Qy square, and Qz. So this is the diagram I have basically showing you here. So we have a Q parallel and then Qz. So Q parallel is this direction and Q perpendicular is basically Qz is this direction. So here I have noted some terms, which is called specular reflectivity, grazing incidence, small angle scattering, grazing incidence diffraction of specular diffuse scattering. So some basically terms I have coined here. What does it mean? So let us start with the specular reflectivity. So now you go back to this diagram. So your incident wave is theta I, which is coming along this with an angle theta I, and then it is going in theta f. So why we can see in reflection, what we suppose a light wave is falling on a mirror. So you can see if we suppose you have a mirror, then sunlight is coming, and then you can see a bright spot at some point. So if you remember, if you can measure, then if you can see that the line rays coming from the sun and the reflection. So these two angles are equal. So that's called the reflection. Basically, it's a reflection of basically incidence angle is equal to exit angle or reflection angle. So when incidence angle is equal to a reflection angle or exit angle, then we have a condition. If you just go this direction, then you have a sine theta I plus sine theta f. So both are positive because we are in the first quadrant. So you will have a sine theta I plus sine theta I. So it will be 4 pi by lambda sine theta, right? But what will happen to the Qx component? Because theta f and theta I are equal, so this will cross. And similarly, Qy will also not be there. So what will happen? In your specular, in a reflection condition, you will have only Qz component, right? So you will have only Qz component and no Qx component and Qy component. So what does it mean? So that means that if you are measuring the sample where your incident angle and the reflection angles are equal, so then you are probing the sample only in the vertical directions. Okay, so that is what we call specular reflectivity. So I am repeating this thing again. So if you're measuring your source sample detector, if you are measuring in a way that the incident angle is equal to your exit angle, then you are only measuring the scattering with respect to your QZ. And that QZ component will give you information along the depth of your sample. So now go back to my initial comment that you want to measure the information of your sample along the depth. Okay, if you want to measure the sample information about your sample along the depth, then you make your sample in a way, you do your measurement in a way that your incident angle and the exit angle remains same. And then you change your sample and then you have a profile, and that profile will give you information of your sample thickness, your sample information along the vertical, along the depth of your sample. You are not considering the lateral spacing or lateral information. You are only considering the basically sample in depth, sample along the depth. So the implication I will come later, but let us talk about some other things. So we said grazing incidence diffraction. So you are along this direction. You are in a Q parallel direction. What I will do in that case? In that case, I will not go along theta F direction, but I will change my theta R. So this angle, this phi angle will change. So what will happen? I will, instead of if you remember my initial diagram, I had a psi along this direction and psi along this direction. So instead of going along this direction, now I am going along this direction. And then you can see that QZ component is 0 because you have a theta, only theta I, no theta F. So basically you have a small QZ component, but your QX and QY component will change because you have a theta F is changing, not theta F, but basically there will be another term which is cos chi. So that will be changing, and that because of that change, your Q component is changing. And then you can say that my information along these directions. So what does it mean? That means you have a sample and you are going measuring in these directions. And then if you are measuring, so that means you are getting information in QX and QY. So QX and QY, the reciprocal of this thing is Rx and Ry. So you are talking about sample information in the in plane of your sample. So instead of that, you previously talked about the vertical information. Now you are talking about the in plane information. So the same sample, just going into different geometry, you can talk about two different portions or do different information, and these information do not basically overlap. So you are talking about one place the sample surface or sample interface information. Another case you are talking about the sample vertical direction changes of the sample. So these are basically, that's why I said that what information you want to talk about the sample surface in plane information, then you have to go in this direction. If you want to talk about the sample in depth information, then you have to go along this direction. And then accordingly, you have to change your scattering geometry. That means you have to go in this direction or in this direction. So this is the thing you have to remember, and that's the plus point of your X-ray or neutron scattering. Okay, now for any scattering, these are all radiation, so you will have a validity of Snell's law. Snell's law, we know that we have an incidence angle and then we have a refractive index and we have refracted angle. So basically we can say if it is an interface, we can say that there will be some refracted, so which goes into the sample, and then some reflection which is coming out of the sample. And the ratio from this we can calculate the basically refractive index. And for X-ray, we can write n is equal to 1 minus delta plus I beta. Okay. This one, what is 1 minus delta? So because n is a complex number. Okay. So probably you do not know, but it is a refractive index, and for refractive index, n is a complex number where the real component is suppose you have a glass. Okay. And we all know the refractive index of glass is 1.5 for visible light, right? Or spec or anything we use glass is 1.5. So that 1.5 is 1 minus delta. This part is 1.5 for visible light. Okay. But we do not know the beta part. Basically, the absorption beta basically denotes the absorption. But for visible light, the absorption we don't care much because we don't need to. But for X-ray, this absorption plays a big role because ultimately it excites, it can generate other kind of source, other kind of measurement techniques you can be used. So you can say N1 plus I N2, where N2 is our beta, which is basically related to the absorption, and N1 is equal to 1 minus delta. And for most of our sample in visible range, not most, all of our sample in visible range, we see N1 is greater than 1. N1 means 1 minus delta is greater than 1. But why I have written 1 minus delta in this way? Because in X-ray, delta, let me see, yeah, delta is you can define your delta in this way. These are calculations. You don't need to, you can just remember this number, that R0, that classical electron R0 is equal to 0 times lambda square by 2 pi into row electron. So for delta, if you suppose you have a carbon material and then you have a row electron for carbon, so delta is a positive number, but the value of delta is of the order of 10 to the power minus 6. So instead of 1.000001 writing, I write 1 minus delta as if delta is equal to 5 into 10 to the power minus 6, 6 into 10 to the power minus 6, something like that. So that's basically the logic of writing 1 minus delta. Now, why 1 minus delta? Because you can see that delta is a positive number. Okay, because here nothing can be negative. Row electron is a Z by V, row electron is the electron number by volume of that electron. I will show you some calculation. And then delta is a positive number. And if delta is a positive number, then if we write 1 minus delta, that means in 1, that real part of the refractive index is always less than 1. This is completely opposite to the visible light. Because visible light, we always go for 1.5, 1.75. So if we go some opticians, then they say that if you have a high power chashma, you go for high refractive index. But this high refractive index is always greater than 1. Basically, you 1.5, 1.7, and probably the best you can get 1.95 even. So because if you have a high refractive index, you can reduce the thickness of your lens. So that's the motive. But in all cases, vacuum is in visible light, vacuum is 1 and all the materials are greater than 1. Okay. But in X-ray regime, vacuum is 1 but all the materials are actually slightly less than 1. Okay, so that's why 1 minus delta, and delta is a positive number. So 1 minus delta is always will be n will be always less than 1. And that's the basic point of your X-ray scattering. So you have big difference from the visible light, that you have refractive index always greater than 1 for your all the samples except vacuum, and for X-rays the refractive index will be always less than 1 and the vacuum will be 1. And also you can calculate the beta. So these are formulas you can calculate, where you have a R0 equal to 2.82, and I said delta X and delta N are of the order of 10 to the minus 6. So similarly, I can calculate for it for neutron, and neutrons it is basically the same formula. I have simplified it with row electron, but beta in neutrons, the beta, the absorption, I said the absorption is almost 0 for most of the samples, except some calcium, gadolinium, and a few. So these are for these samples. So these are basically, so it's very hard to stop neutrons. That's why working with neutrons are much more difficult job than the X-rays. X-ray basically absorbs, and then you can terminate your beam. Okay, now let us, because I am running out of time, so let us calculate. Because these are simple formulas where you can actually, but let us calculate this row electron, because that will give you some feeling that why X-ray and neutrons are different. Okay. So you know this kind of structure. You have a FCC, BCC, or hexagonal structure, and there are plenty of examples of crystals that have hard matters that have this kind of structure. And similarly, you have a soft materials like carbon, which has a diamond crystals, and carbon has different amorphous to diamond, all kind of structure. So these are different type of structures that people have investigated over the period of 100 years and so. And then you know that gold, okay, gold is my FCC structure, and this iron is my BCC structure. So this kind of structure, BCC means body-centered cubic, FCC means face-centered cubic. So these are the structures we know about. But how to calculate row electron? This is very simple. That's what I like to show you these slides, and then I'll go for neutrons, and then I'll stop it here today probably, so that you can ask some question. So let's consider gold. Gold Z is equal to 79. So if you see this formula, Z by V, row electron is equal to Z by V. So Z is equal to 79, and then gold is a FCC structure with A basically this distance is 4.07 angstrom. So if you calculate, so in a FCC structure, you have 4 atoms in a unit cell. Okay, so this is very well things, and you don't need to remember much. So this you have 4 atoms in this crystal, basically in this unit cell. So basically you have a volume of 67.42 angstrom cube. So what you do, you write 79 times 4, that is the number of electrons in this whole unit cell, and then you can divide by the volume 67.42, and you can get the electron density of 4.687 electrons per angstrom cube. And immediately you can calculate, you can put this thing in here. Only thing you need to know what lambda you are measuring. So suppose you are measuring in copper K alpha, which is 1.54 angstrom. So you can calculate delta. And then from that delta, you can calculate your all the things, whatever you want to know. So diffractive index and all these things you can calculate, and then you can do other things. But similarly, you can do it for neutrons. So neutrons, this instead of Z is equal to 79, now the formula is basically rho I times Bi by Ai. So I is the element because I is gold here. So basically I can say that this is my B. B means scattering length for my neutrons, and this is a kind of thing that people have done it. So people for each element, people have calculated the scattering length. So you don't need to think about anything because in X-ray you only need to know the Z, which is the atomic number. You need to know. But for neutrons, you need to know the scattering length. That's all, basically. So you can do the similar things, and then you can see that 0.451 into 10 to the power minus 5 Armstrong square. So here you can see 4.687 into 10 to the power electrons per Armstrong cube, but you are forgetting that you are here one R0 terms is multiplied, here R0 terms are not there. So basically, if you multiply 2.82 10 to the minus 5, then you multiply with 2.82 into 10 to the minus 5. So you can see that it will give lot of scattering because your scattering will be 2.82 times 4.687, whereas it is 0.451. So the same gold for X-ray will give lot of scattering, while for neutrons, it will not give that much of scattering because scattering length density is small. So this scattering length density or scattering this B factor or rho factor, this will actually dictate you how much scattering you will be getting from the sun. I'm going through another example. So suppose you have a stearic acid. Now I am calculating this thing for a soft metal molecule. So this is a stearic acid structure. So you can think of that it is basically a cylinder of 20 Armstrong square and which has a length of 24 Armstrong. So the volume will be 20 times 24 is a 440 Armstrong cube. And you can calculate the number of atoms, the number of electrons. So it has carbon, 17 carbon COOH. So, and then you can see that you can calculate the total number of electrons and then total number of electrons by this thing. This is 0.33 electrons per Armstrong cube. So you can multiply 2.82. So it will come down to something like 1 point something. Whereas if you do it for neutron, then it is for hydrogen, this is important. So for hydrogen, this is minus 3.74 femtometer. For carbon, it is 6.65 and for DO. So you do the same way as you did this thing. And then you can come out with 0.265 to the minus 5. But here the importance comes for Newton's scattering. So you have H, which is minus 3.74. But if you just replace this H by D, then this B of D is 6.67. So what you are calculating here, minus 0.265, will become plus 0.587 for your D atoms. So just replace this hydrogen molecule with deuterium, and you have a lot of scattering from your stearic acid. So by isotopic substitution, we can change the scattering. So you prepare a sample which is a hydrogenated sample. You prepare a sample, same sample, which is a deuterated sample. And you do neutron reflectivity or neutron scattering. You can see that the huge difference in scattering. And that way you can actually probe much better, which you cannot do this thing for X-rays. Because for X-rays, if you just replace this hydrogen by deuterium, then you will have another electron only. So instead of 160, it will be 195. So your electron density will be 0.33 to 0.35 or something like that. So you are not actually changing much your scattering in X-ray. Whereas in your neutrons, you are actually changing a huge scattering. And that is the main advantage, one of the main advantage of using neutron for biomaterials, that for isotopic substitution, you can actually determine the more specific information of your sample. And that is basically the part I want to say, that each probe has definite advantage and you like to use that probe for. So basically I can stop it here because I can go further now. Time is 5:45, so that if you have some questions, then I can say. So otherwise, because you are not talking, you are not. So maybe we can start from this slide in the next class. Okay, so I have stopped sharing now. Yeah. Now, do you have any questions? Chat box. Questions. Is it too hard for you or is it too simple for you? At least you can reply to this one. Any question?
No questions, sir, yet.
No question here, right? Okay, so should I stop this thing now or what should we do?
So we'll wait for 2 more minutes.
Okay.
Then we'll start.
Okay.
So no more questions, sir. We'll end the meeting today.
Okay. Okay. Let us end here and then we'll next class on Friday we'll talk. Okay.
Sure, sir. Sure.
Okay. Thanks. Thank you. Bye.